Are there any questions? Are there no questions? You know, going back to this problem number 18, I was looking back at the way, actually I've done this problem many, many times, but in the past I've had people carry 2 extra digits, you know, and doing the calculations, and that's the way I used to do it, but I was thinking, yeah, it takes too much time, so I was going to cut it down to 1 extra digit, but in this case it made a difference. And so, you know, that last error was just a dropping digits round-off error, and you wouldn't be deducted for that, you know, if the calculation is correct. If the calculation is wrong or you did too much rounding, then you would be deducted for that. And so let's move on to next. The next question involves something called the Chatelier's principle. Just take a look at this. Here. All right, what Le Chatelier's principle involves is, let's say you have a system here, and this is at equilibrium. The reaction here is sulfur dioxide, 2 of those plus an O2 yields 2 SO3. And so this is the proper equilibrium mixture, that is, after this has gone to completion, these are the stable amounts or molarities that will exist in the flask. In Le Chatelier's principle, what you do is you perturb it or you upset that equilibrium. One way to upset this equilibrium is by injecting more sulfur trioxide into the flask. Now, if we inject more sulfur trioxide, then what happens is we got too much sulfur trioxide. And so, in other words, if we add more product, you know, the ratio is going to grow, it's going to get too big, and what's going to happen? Yeah, there's going to be a shift. And in this case, the shift would be to get rid of some of the products in the form. And so we can see here, we start off with 1.68 moles of SO3. There's a shift to decrease the amount of product. It goes down to 1.46 and reestablishes equilibrium here. And so this is an example of Le Chatelier's principle. We can summarize it like this. So if we add or remove a gaseous reactant or product, so if we add or remove, if we add gaseous reactant, it's going to be too much reactant, screws up the ratio. If you got too much reactant, you better form more product or get rid of some of that reactant so it shifts to the right. If we remove reactant, then we have too little reactant, it's got to shift to the left. And so we just think in terms of these shifts, you know, and how these things upset the ratio. Shifts left or right to compensate. Number 2, add an inert gas. If we add an inert gas, will that perturb this equilibrium? That is, upset it. So let's take a look at this. What if we add, let's say, 2 atmospheres of nitrogen gas to this? If we add 2 atmospheres of nitrogen gas, then the total pressure in the flask is going to be quite big, right? But will that impact this equilibrium? And so if I add nitrogen gas, does that increase the amount of reactant or decrease the amount of reactant? No. Does it change the amount of product? No. Nitrogen doesn't participate in this equilibrium, so if I add something that's inert, nothing's going to happen. There's going to be no change in this equilibrium. But the pressure will still change. The pressure will change, but the equilibrium will not change. The total pressure is going to increase dramatically. Let's say. Okay, change the pressure by changing the volume of the system. Now, if we change the volume of the system, will that, let's say, you know, if I add more reactant, that's definitely going to change the reactant. So if I decrease the reactant. It's going to change the reactant side again. But what happens if I just go from 10 liters to 20 liters? If I go from 10 liters to 20 liters, then it's going to cut all the concentrations in half. And so if I cut all the concentrations equally in half, will it still be at equilibrium? What do you think? Right. It might not be. It depends on the coefficients. If you look at this particular reaction, here, we have a total of 3 moles of gas as reactant and 2 moles of gas as product. And so if you expand the volume, it tends to favor the side with more moles of gas. And so by expanding the volume, if we doubled the volume here, the equilibrium would shift a little bit to the left because this side favors more moles of gas. Whereas, let's say we went from 10 liters to 5 liters. If we compress the volume, well, then smaller volumes are going to favor fewer moles of gas. And so smaller volumes favor product, larger volumes favor reactant for this specific reaction. Now, if we went from 3 moles of gas to 3 moles of gas, then does it favor either side? No. And so if we go 3 moles of gas to 3 moles of gas, then changing the volume is not going to upset anything. It's just when we have an imbalance in the number of moles of gas that we'll see a shift. All right. So let's go back to the homework and take a look at this problem here. Number 40. And so number 40, we have N2O4, NO2 equilibrium. It's here. And in fact, this mixture is currently at equilibrium in the brown container. So this is just the right amount of N2O4 and NO2 to maintain a state of dynamic equilibrium. And this mixture on the left is allowed to expand into the evacuated flask on the right. And so what we're going to do is we're going to open this valve and let this expand here into the container. Is that going to upset the equilibrium or not? And so we look. Well, what we're doing is we're cutting the concentrations of both of these, but we're cutting them by the same amount, right? We're increasing the volume here. And so if we expand the volume of the container, is that going to favor one side or another, or are we just going to have the same equilibrium? It's going to favor one side, and it's going to favor which side, the product or the reactant side? It's going to favor the product side because the product side has 2 moles of gas, the reactant side has 1 mole of gas, so it should favor. And so if we expand this, it's no longer going to be at equilibrium. The equilibrium will be perturbed. And so in Le Chatelier's principle, we try to figure out what the new equilibrium will be. And the new equilibrium, we should see a shift to the right to produce more product to compensate for the larger volume. And so let's try out a calculation for this. Well, the first thing is, let's just take a look at this side and just verify that this is at equilibrium. And so the reaction here is N2O4 gas decomposes into 2NO2 gas. And they're saying my initial conditions are already at equilibrium, but we could check this. The initial conditions will be 0.971 moles of N2O4 over 0.750 liters. So let's go ahead and calculate the concentration for that. 0.971 divided by 0.058. Does someone have their calculator handy? Just punch this out for me. What do you get? $1.294. Okay, 1.294. Thank you. Molar. And what's the NO2 concentration? It's going to be, oops, did I do that right? Sorry, I didn't. No, that's right. The NO2 will be 0.058 divided by 0.75. What does that come out to? 0.07733 molar. And so they're saying that this mixture is at equilibrium. And so what we can do is we can just verify this. How can we verify that this is at equilibrium? We can calculate Q. Q. So let's go ahead and calculate Q for this. And then just make sure. So Q is going to equal the NO2 concentration squared initial divided by the N2O4 concentration initial. And so what does Q come out to? So square this divided by this. Zero point 0.004152. About 3 sig figs. 4152. And then we compare that to 46. 46. All right, let's write that down. Because it's 4152 and it's supposed to be 461.
Yeah, that's sorry.
Yeah, and so yeah, maybe there's a calculation error.
Yeah.
So it came out 4617. All right, this is more like it. Although 4617, it's supposed to be 461. Is this really at equilibrium? What might have happened? Well, a couple of things. One, we dropped. How many digits did you end up dropping? Was it 400000 after this? No, we ended up dropping, right? If we drop digits, it's called round-off error. And the same thing over here. Round-off error, correct? And so that could be it. Or two, these were rounded, the moles here, volume. And so would you expect this to be within round-off error for 462 versus 461? Oh, can you check the valve and just try to shut it? Clockwise. All right. Was it open?
No, but it smells like gas now.
All right. If it still smells like gas, if it doesn't dissipate, open the hoods. Right, the hood door right there. Just lift it up, and that will draw out some of it. Is it? Yeah, that should be good. If that doesn't take care of it, we'll take a look at it in a minute. All right, so this looks like it's close enough within round-off error. Sometimes if you're ever uncertain, you can just carry extra digits, as we've done earlier. So this is actually at equilibrium, initial equilibrium, right? And then what we're going to do is we're going to perturb it. And the way we're going to perturb it is actually increase the volume. And so when we open this valve, then the total volume is not 3/4 of a liter. The total volume will be 2 1/4 plus 3/4 is going to give me 3 liters to 3 sig figs. And so the total volume is going to be 3 liters. And so here we are going to perturb it by increasing the volume. We increase the volume, that changes the molarities. And so let's figure out the new initial conditions, or the perturbed. You know, this is going to be perturbed at equilibrium. We'll see. And so rather than taking 0.971 and dividing it by 0.75, we're going to take 0.971 and divide it by 3. And so can you do that for me and tell me the number 0.971 divided by 3? 0.3236. Okay, so I've been just carrying 1 to make, again, to make it quicker. Even if it's a 6,6, we're going to drop the 6 here. And then the NO2 is going to be 0.058 divided by 3. .01933 molar. Thanks. All right, so we already know what's going to happen. When we increase the volume, this should shift. When we increase the volume, the equilibrium is perturbed, and to reestablish the equilibrium, it should shift to the right to produce more product, or shift to the left. Right. It should shift to the right, and so we see that. And so what we're going to do is we're just going to confirm this, you know. And so this system was at equilibrium, but now let's see. Let's go ahead and calculate Q for this. Q is going to be 0.01933 squared divided by 0.3236. And so what does our Q come out to here? Point 0.001154.
Yeah.
All right. So it's too small. It should be 461. It's 115. Too small, which means we need more product. And so calculating our Q confirms what we already predicted qualitatively. It's got to shift to the right. When it shifts to the right to reestablish equilibrium, we're going to go minus X molar plus 2X molar here. And so we have to build up a little bit of more product and lose some reactant. So we're going to end up with 0.3236 minus X molar, 0.01933 plus 2X molar here. And now we want to solve for X. Okay, so solving for X, we can use K to do that. Kc is going to equal NO2 at equilibrium squared divided by the N2O4 concentration at equilibrium. So the NO2 concentration at equilibrium is going to be 0.01933 plus 2X squared divided by 0.3236 minus X. And this should equal 0.00461. So what we have here is just some algebra to complete. What would we do from here? We'd probably get it into quadratic form. Then solve. Did I talk about the simplifying assumption? No. Okay, there's actually, I think I skipped one problem, but it's okay. There's a trick that we might be able to do with this particular problem. to make the math a little bit easier. And the trick is going to be this. So alternatively, this is not so hard to solve, but alternatively, try resetting the initial conditions. There are two reasons to reset the initial conditions. One, it makes the math easier. Because what it does is it creates more zeros in the initial molarities or pressures. It makes math easier by making more zeros for the initial. All right, this one. And 2. It for certain problems, it is the only way to solve it. Because of calculator rounding error. So let's say, to give you an example of calculator rounding error, let's say you had something like a 99.9999999% change. And so you had almost 100% change, right? But how many digits does your calculator carry? Do you know? 8 digits? If you have an 8-digit calculator, what if you have a 99.9999999% change? And so now we have 9 digits. If you have 9 digits, all 9s, but your calculator only carries 8 digits, what's going to happen? It's going to round it to a 100%. And so the problem runs into this. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Your calculator is okay with this, right? But let's add on one more digit. Let's go with 8. And so it's a 99.9999998. Let's say percent change. But your calculator is only capable of registering 8 digits. What's it going to do to this 8? It's going to drop it, right, because it can't show it. And it's going to round up or round down. Or in other words, leave it, it's going to round up to, and so your calculator is going to show this as 100. That's 3, 4, 5, 6, 7, 8. It's going to be rounded to this. And so this is what we call a calculator-based rounding error. It's supposed to be this, but your calculator is going to show this. Does that make sense? So why does it matter? Let's look at a scenario over here. Let's take a look at something like this. In this example, let's say that the K is equal to 10 to the minus 10. If you have a K value that's 10 to the minus 10, right, what does that say? It says that you have practically all reactants and very little product. And so the way you could visualize that is having a water well with two sides. We have an uneven water well. And so this is going to reach equilibrium. When it reaches equilibrium, you know, both sides are going to be the same level, but if you look at the reactant side and compare it to the product side, you'll see that the reactant side is heavily favored. Most of the water is over here, right? And so let's say we have 100 gallons of water total. Then I would say like 99.99999% of the water is over here, right? And then a very small percentage of the water is over here. In other words, in Chem 1A, when K is 10 to the minus 10, we say that there is no reaction. And so Chem 1A, you would have said there's no water over on this side because it's such a small K, you assume, no reaction, no driving force, no reaction, right? But in Chem 1B, we say, a little bit of product does indeed form, and we want to know what that little bit is here in Chem 1B. All right, to make your life easier, sometimes what we do is we reset this. And so here, if I perturb this, let's add some more water. I perturb this and add more water, like this. What's going to happen here? Well, I added more reactant, it's going to shift to the right. And so if I add more water here, it shifts to the right to reestablish a new equilibrium, and the new equilibrium will look like this. Am I going to gain reactant or lose reactant? Well, it depends on what your initial is. If your initial is the original initial conditions, then we actually gain reactant. Okay, this level is going to drop a little bit, this level is going to rise a little bit. If we look at it from the perturbed initial, then we lose. And so it depends on the context. Sometimes we say we lose reactant, sometimes we say we gain reactant, depending on if you're looking at the original initial conditions or the perturbed initial conditions. And it depends on the problem, because some problems are going to ask you, did it gain or lose? And then you have to figure out from what reference point are they talking about, the perturbed or the original. The products will gain. There's no problem. This side's going to go up. And so we'll end up with this new equilibrium. And the new equilibrium is going to have more water on the reactant and more water on the product compared to the original. Or it'll have less water on the reactant and more water on the product compared to the perturbed. All right, what we can do here, though, is this. You know, we're going to figure out the change. In this case, the change from the perturbed will be minus x. The product will be plus x. whatever it is. Minus, plus. That's one way to solve this. But what we can do to make this maybe a little easier is do this. Let's say we have 100 gallons here, and then we add 10 gallons of water here. And so we have 100, oh actually this is a total of 100 gallons for the whole thing. And so we have a total of 110 gallons of water. And so the whole concept of resetting of the initial conditions is this. We have two ways we can reset. We can reset to the left. If we reset this to the left, what we're going to do, let me blow this up. Is we're going to put all 110 gallons of water on the reactant side. And so this will be 110 gallons here. And then over here on the product side, we'll have 0 gallons. And so this is what I mean by getting more zeros in the initial condition, because if you look at the product side, there's 0. Reactant side, it's all there. When I open this here, will I reach the same equilibrium as I would have before? As long as I have the same amount of water, you know, it doesn't matter if I put 30 gallons here, 40, whatever. As long as the amount of water stays the same, then I should reach the exact same equilibrium. Versus this. If I reset it to the right, here, then I'm going to put all 110 gallons of water on the product side. Say this is 110 gallons, and this is 0 gallons here. So if I have 110 gallons over here, 0 gallons there, or 110 gallons on the left, 0 gallons on the right, when I open this and let the water flow, will it reach a different equilibrium or the same equilibrium? It will reach the same equilibrium. And so either way I approach this, it's going to be the same equilibrium. The same equilibrium results. And so by getting more zeros in the initial conditions, then you get rid of more binomials, because if you have initial concentration plus or minus x, you're going to get a binomial, and those binomials are more work algebraically. Whereas if you have a 0, it's just going to be plus x or plus 2x, and there'll be less math involved. The other thing is this. We want to reset. This is preferred here for this setup. Why is this side, why is this one preferred? The reason this is preferred is, how many gallons of water are going to leak over here? Not much, right? Not much. Whereas if I open this, how many gallons of water are going to leak over here? Practically all of it. And so if I have something like this and I calculate my x, what is my x? My x is going to be 109.9999999 gallons. And if you have an x that's almost the same as this and the 9s keep going, what's your calculator going to do? It's going to round it to 110 gallons. And if your x is 110 gallons, we start off with 110 gallons over here. We do minus x, we lose all of it. And so all 110 gallons goes over here, and this becomes 0. Is that right? Is that at equilibrium? No. And so this is what we call the calculator rounding error that we want to avoid. And it occurs, you know, it's not that often, but it occurs sometimes where you aren't going to get the right answer. There's no way you can get the right answer without having to reset it, because your calculator continues to round it and give you the wrong answer. Whereas over here, your calculator is going to have no problem, because let's say only 0.00001 gallon leaked over there. Well, that's no problem, because it'll do 1.000 times 10 to the minus 8 or whatever gallons. And we aren't going to have that problem. And so for this Le Chatelier's homework here, let's try a different approach. The approach that we just did was we took the original equilibrium and perturbed it to get a new set of initial conditions, and then we just looked at the shift. You know, the Le Chatelier's shift was going to be a minus x plus 2x, and then go from there. And so let's go back to that original problem. N2O4 gas goes to 2NO2 gas, and then look at the perturbed initial. Kc for this was 4.61 times 10 to the minus 3. And what were the perturbed initial concentrations again? 1.294 molar. And the NO2 concentration? 0.07733. 0.07733 molar. When you look at this K value, does this K value favor reactants or does it favor products? Reactants. You know, it's a kind of a small number, and so it should be mostly reactant. And so this is one thing we can try here to make the math a little bit easier, is we try to reset the initial condition. Now we have a choice. We could reset it to the left or we could reset it to the right. How should we reset it? And so rather than pushing all the water to one side, we're going to push all the atoms to one side. And so we could convert all these nitrogen and oxygen atoms that were reactant over to the product side, or we can convert all the nitrogen and oxygen atoms on the product side to the reactant side. So which way should we go? To the reactant side. And so we're going to try to shift all the water to the left. In other words, we're going to go plus 2, and when I reset I use y, plus y, minus 2y. When I reset, I look for the limiting reagent. What's the limiting reagent? Well, there's only one reagent, so that's the limiting reagent. And the limiting reagent is going to go down to 0. And so this goes down to 0 molar. And that means 2y is 0.07733 molar. If 2y is that, then y must be half of it. And so it's got to be 0.07733 divided by 2 molar. And so if I add that, all those nitrogen and oxygens, what's the new molarity of N2O4? Can someone calculate it? And so just do 0.07733 divided by 2 plus 1.294. 1.332 molar. I'm just going to stick with my using one extra digit. And see if that works. All right, so what did I do? Well, I created the 0 in one of the initials. That means I have one fewer binomial I have to worry about. And so which way is this going to go now, the reaction? To the right. And so this is going to be minus x molar plus 2x molar. And so at equilibrium, I'm going to get 1.332 minus x molar and 2x molar here. So now let's plug this back into the K C expression and C. What we have now, we have 2x quantity squared divided by 1.332 minus x. And so is the math a little bit easier? Yeah, it's a little bit easier. We don't have to square a binomial now, right? And that saves a little bit of time. And so the math is a little bit easier. One less binomial. But still quadratic. Uh-huh.
Question. You know that 0.0773 molar divided by 2? Can you explain that one more time? The y equals.
Okay, if 2y is 0.07733, then y is equal to half of that. That's where I got it. Uh-huh.
What about the negative? So minus 2y.
Oh, you're right. This is a minus 2y, and so this means that this is, negative 0.07733.
So the initial would be 1.294 minus.
No, plus y.
Plus 1.y.
Yeah, so negative 2y is negative 0.07733, therefore y is 0.07733. All right? Are we good? Now, when we think about this, when we reset it, this is like having two uneven wells, right? And having two uneven wells, the reactant well is more favored because if you look at it, it's 10 to the minus 3. 10 to the minus 3 is 1 over 1,000. And so it seems like the reactants are quite a bit more favored. And so if we reset all the water to the left side, now that's what we just did. And now we're going to let the water flow to the right, or at least the atoms move to the right. When we do that, are we going to expect much of a change? This is the reason we reset it to the left. If we reset this one to the right, then there would be a more significant change, correct? And so there's one more trick that we might try to do. And that is, by resetting this, we're resetting it so that it looks more like the equilibrium should be. This equilibrium is favoring the product, not the product, it's favoring the reactants, and that's exactly what we did. We favored the reactants fully. And so what I'm going to do here is we're going to do one more thing. Oops. To simplify the math. And the one more thing that we're going to try is called the simplifying assumption. Okay, another method for simplifying the math is called the simplifying assumption. SA. And the simplifying assumption goes like this, you know. If you have a swimming pool full of water, and you remove a drop, let's say I take out one drop of water, and so swimming pool minus one drop of water, is it going to change the volume of the swimming pool much? No, in fact, you'd say one drop of water is negligible. You'd say it's negligible compared to the volume of a swimming pool. And so that when you take a swimming pool minus one drop, you just end up with the same thing. That is, it really didn't change. We still call it the swimming pool. Versus if we took out half the water, then we call it half-filled swimming pool, right? But you'd still call it a full swimming pool, wouldn't you? Even though it's missing a drop. This is called the simplifying assumption because you wouldn't bother recalculating the volume of the swimming pool, would you? If somebody took out one drop? No, it's no big deal. Well, we could try it here. And so there are two options here. We'll just go ahead and get it in the quadratic form and solve. Or we'll try the simplifying assumption. If we try the simplifying assumption, SA, then it's going to look like this. We're going to call this our swimming pool. 1.332 is our swimming pool. And let's say X, imagine X as being 0.0000001. Is losing 0.00001 going to have any impact on that number, really? No. And so we're going to pretend that X is like a tiny drop compared to this. And therefore, we can kind of ignore the X, the change in this here. And so in our simplifying assumption, this is what we'll do. Here, oops. Into the camera, sorry. We don't know if it's valid because who knows if 1.332 is like a swimming pool of water and X is like a drop, but we're just going to go ahead and assume it. And so we assume that X is much smaller than 1.332. If we make this assumption, then that means that means 1.332 minus X is about the same thing as 1.332. And so using the simplifying assumption killed off this binomial, and we're just left with 1.332, which makes the math a lot easier. What about the 2x? Can we just assume that's 0? So in other words, this would be like this. This would be a drop in the swimming pool. And so now we have 2 drops here. With 2 drops, can we just go ahead and assume that's nothing? It's 0? In this case, we can't because is 0 equivalent to a swimming pool? What would 0 be equivalent to? Nothing. And so this is like, okay, you have a swimming pool, you lose a drop, but this would be like you're out in the hot desert and you've been there for months, and the 2 drops of water, would that be significant? Or you're on some planet, there's no water, at least you have 2 drops. Is that significant? You're going to treat that like nothing? No, it's significant. And so here, anything compared to 0 is nothing, absolutely nothing. Anything compared to 0 is significant, even if it's a very small number. And so here, the 2x does not drop out. And so what we'll do is we'll simplify this. Kc equals 4.61 times 10 to the minus 3, which is going to equal 2x quantity squared. This we can't ignore. That's significant compared to 0. But this we can ignore because it might be insignificant compared to this. Now, do we have to use the quadratic equation to solve this? No, all we need is the square root key on our calculator, right? And then we can calculate it. And so this simplifies the math greatly so that we can avoid the quadratic entirely and then solve for x quickly. And what does x come out to? Here. .20,
7552.
okay, 0.2075. We're only allowed 3 sig figs, so we'll just go 0.2075. All right, now what we have to do is we have to justify our assumption. So let me do that over here. Okay, after calculating x, we must justify our assumption. The justification is kind of weird because the justification is going to use this value of x, which is wrong because we made this assumption, and then justify its use. And so it's kind of like a circular justification. And our circular justification is this: the percent change based on x must be less than 5%. And so in other words, it has to be a small percent change. That is, losing a drop out of a swimming pool is a small percent change, but if you start losing 5% of the water in your swimming pool, is that significant or insignificant? That's significant. And so there, we think differently. And so even if it's getting close to 5%, that's getting kind of big. And so the percent change is equal to the change over the initial times 100%. Now what is the change in this case? The change is x, the initial is 1.332 times 100%. And so x, did somebody double check that calculation there?
Yeah, actually I got it wrong. X should have been 0.02.
Okay, 0.0294.
Yeah.
One more digit.
1.
1. Is that what other people got?
No.
Zero- 0.039? Well, it sounds like most people got 0.039, so let's try that. 0.03918. All right, so what we're going to do is we're going to plug in 0.03918 divided by 1.332 times 100%. That gives me what percent change? 2.9%. Well, this is less than our 5% cutoff, so are we justified in using this? Yes. We're justified in using it, but 3% is getting close to 5%, which means the error is going to be kind of big. The closer we get to 5, the bigger the error becomes. Where this works great is when we have a percent change that's like 10 to the minus 16% change. If you're getting like even 10 to the minus 5%, if you're getting something like 10 to the minus 5% change, there's no difference in making the simplifying assumption versus solving the quadratic equation. When you're starting to get over 1%, 1 to 5%, then if you do the full quadratic, you're going to get a better answer, a more accurate answer. Does that make sense? But this is still acceptable because it's close and it saves you a lot of time. Especially on timed exams, you're always worrying about, am I going to finish? And so this is going to give you a fairly close answer. Whereas if you're at 6%, 6%, you're just pushing the limits too far. The amount of error you're introducing is too big. But we're okay. We're okay to use the simplifying assumption here because it's less than 5%. And so, since we're okay to use the simplifying assumption, what should I say is my equilibrium concentration of N2O4? Right here. Because I said that that the equilibrium concentration here, X is insignificant, right? And so should I just go ahead and ignore X and call it 1.332 molar? Because the simplifying assumption is valid? No, because that would add another error on top of the error that we just introduced. And so what we do is we go ahead and use the X to calculate it. So it would be 1.332 minus the X value of 0391. 0.0391 sub 8. And so let's carry that over a couple of 1.2928 molar. 1.2928 molar. And so we did lose a little bit. We went from 133 to about 129. And then 2x, this is going to come out to what molarity? So we just double that. We get 0.07836 molar. Here. So now we calculate the concentrations. What should we do next? We should double check the equilibrium concentration by calculating K based on these. And so if we calculate K, it's going to be 0.07836 squared divided by 1.2928, and hopefully it equals 4.61 times 10 to the minus 3. What does it come out to?
4.749.
749 times 10 to the minus 3. 4.74, so 474 versus 461, it's kind of off, isn't it? It's off. What's that?
But it makes sense that it's off.
It makes sense that it's off because we did use the simplifying assumption, right? And so it's going to be off. And so the simplifying assumption, how well it works depends on that change. And in this case, the change was a little bit too much for it. And so it's close, but quadratic with, if these calculations are accurate, quadratic without SA would be better. We always try the simplifying assumption if it looks like it might work. The reason we always try it is because it's so quick. You know, it doesn't take very long to use the square root key, you know, versus going through the whole quadratic. And then, you know, when you do the justification again comes out to a very small percentage, then it wouldn't have mattered if you did it quadratic or the simplifying assumption, you would have come up with the same answer. And so what I want you to do is just try this using the quadratic to compare. And so solve it without the simplifying assumption, in other words, and see how good the answer comes out. I'll let you do that. Let's take a look at another problem here. But on timed exams, you know, this will save you some time and you'll get a close answer. Which is better than leaving anything blank. Yeah?
What could you plug out if you get an imaginary number?
What if you do the quad?
A negative inside the square root.
Then there's something wrong. You can't. Yeah, there's got to be a calculation error. That will never come up. All right, let's move on to another problem. Okay, let's take a look at these two reactions. Here we have two chromium 3s, cadmium. What kind of reaction is this? Metathesis? This is a redox reaction. What's the oxidizer? Chromium 3 or cadmium? Chromium 3. Chromium 3 is taking electrons from cadmium. So chromium 3 is the oxidizer, cadmium is the reducer. Okay, now we compare what's the oxidizer on the product side? The cadmium. And so this is a kind of a competition between chromium 3, the oxidizer, versus cadmium 2, and cadmium, the metal, versus chromium 2, the reducer. And so which side wins? Is there a clear winner and a clear loser here? And when you look at the Kc value, you'll see it's around 0.288. Does it clearly favor one side or the other? Not really. And so that means chromium 3 and cadmium 2 must be pretty evenly matched, right? Since it doesn't favor one side or the other. All right, now let's take a look at this next reaction here. We got chromium 3 versus, well, what? And so this is another redox where we're taking chromium 3 and oxidizing lead. And so here the chromium 3 is the oxidizer again, but when we compare the two, chromium 3 versus, what's the oxidizer on the right? Lead 2. And so chromium 3 versus lead 2, is there a clear winner? Is one clearly stronger than the other? Now take a look at the Kc. The Kc is 10 to the minus 10. Typically when we think about 10 to the minus 10, we say no reaction, right? In Chem 1A we would have said no reaction. In other words, we would have said this. We would have said that we're going from weaker to stronger. And therefore, if we're going from weaker to stronger, there's no driving force, there should be no reaction. But in this case, in Chem 1B, we're going to find out, well, even though we say there's no reaction, a little bit of reaction can occur. And what we want to find out is, what is that little bit of reaction that can occur? And so let's go ahead and do number 44 as the next example here. So we're taking some lead metal and chromium 3 plus. And this should produce some lead 2 plus and chromium 2 plus. So we'll need 2 chromiums here and 2 chromiums here. Kc is 3.2 times 10 to the minus 10. It said lead metal is added to 0.100 molar chromium 3 plus AQ. What are the lead 2, chromium 2, chromium 3 concentrations when equilibrium is established in this reaction? And so let's go ahead and complete this table. 3.2 times 10 minus 10. Let's put this on. So Kc 3.2 times 10 to the minus 10 clearly favors the reactant side. And so how much lead do I have? 0? Initially they gave us 0.100 molar chromium, and then they said lead metal is added to that solution. And so how much lead should I put in? They said lead metal is added to the solution. An excess of lead. In fact, we need enough lead. Lead is actually a solid. Is a solid, does its concentration change? No, it's going to stay pure. So whenever we have a pure liquid or pure solid in a Kc or Kp, we just ignore that column here. And so we don't put anything. We just got to make sure we have enough lead to reach equilibrium. That's all we need. And so usually we have excess lead, and chromium 3 will be our limiting, or we just have stoichiometric lead. Chromium will be consumed. we have how much lead 2? 0 molar and 0 molar. Okay, now we asked, should we reset this? You know, should I reset, because now all the atoms are on the left. Should I reset it and push all the atoms to the right? Sometimes I want to do that, but in this case I don't want to do that. Why? Because if I push all the atoms to the right, then I'm going to expect a huge reverse reaction, because this Kc tells me at equilibrium most of the atoms should be on the left, right? And so this makes no sense to reset, but that's one of the first things we check. Does it make sense to reset this? So we don't want to reset it. Is that clear for everyone? All right. Now the next step is, let's complete the table here. Which direction should this go? This is going to go in the direction of the 0, so we're going to go minus 2x molar, plus x molar, plus 2x molar. And so at equilibrium, we're going to have 0.100 minus 2x molar, x molar, and 2x molar here. All right, Kc here, this is going to equal the concentration of lead 2 at equilibrium times the concentration of chromium 2 at equilibrium squared divided by the concentration of chromium 3 at equilibrium squared. Okay, we have those values here in terms of x, and so Kc is going to equal x, which is the lead, times 2x quantity squared, which would be the chromium 2, divided by 0.100 minus 2x squared. And so this just looks like a quadratic, right? We got to multiply out this binomial and then get it into quadratic form. Ax squared plus bx plus c, right, is equal to 0, and then either use the quadratic formula or your calculator to solve that, correct? Which isn't difficult, but it takes time, right? To get this into quadratic form takes time, and to solve the quadratic equation takes time. And so is there a way we could try to speed things up a little bit? Make the math a little easier? Is there a way we could try, something we could try to the simplifying assumption. Let's try the simplifying assumption. And so we're going to try that. We'll try the SA, which stands for the simplifying assumption. The simplifying assumption here is going to just say that, you know, this is like a swimming pool, 0.100, and I'm just going to lose a tiny drop out of there, and so it should stay at 0.100. Can I say this is like a swimming pool, 0? No, this is like an empty swimming pool. At least you're adding some water there, so it's a start, so it's significant, right? And so the only thing we can say is that 2x we're going to assume is much smaller than 0.100. This is just a guess, right? We're just guessing because we don't know, but we're going to try to justify it later. It's our guess. And so if we use the simplifying assumption, then the math becomes very easy. And so this is why it's one of the common things that we try to do, especially if you think the change is going to be small. Because we think the change should be small because this should be all, most of the atoms should be all on the reactant side. And so we really do think it's going to work out okay this time. And so actually, this isn't even a, you know what? I was wrong here. Because this is not a square, this is a cubic. And so if we don't use the simplifying assumption, then do you know how to solve cubic equations? We get in cubic form maybe. That is ax cubed plus bx squared plus cx plus d is equal to 0. Do you know how to solve these equations? Yes? How do you solve a cubic equation? Do you graph it? Or do you factor it? What do you do? Factor, whatever. Or you could use your calculator. You know, it turns out that the FX115EF solves cubic equations too. And so if you have a calculator, you can just plug in A, B, C, and D, and it'll give you your x values here. But the Casio FX15ES stops at cubic. It wouldn't solve fourth order, fifth order, or anything beyond. And so potentially you could use your calculator to solve this. But still, getting into cubic form takes time, so it would be nice to try the simplifying assumption to see if our life will become much easier. And so trying out the simplifying assumption, we're going to get 4x cubed divided by 0.100, and the 2x's drops out and gives us 0.100 squared. Now you don't have to buy the $20 calculator to do a cube root, right? You could just do the $8 calculator for that. And so the math becomes very easy, and x is equal to so it'd just be 0.01 times 3.2 times 10 minus 10 divided by 4, and then the cube root. Look down. What do you get for x? 0.0002. Okay, we're allowed 2 sig figs, so give me some more digits.
That's all that shows up.
That's all that shows up, so it'd be 2 0 sub 0.
We got 928.
928.
No, it's 10009.
Okay, 0000928. 40 quadruple 0928.
Yes.
Let's see what.
Yeah, I didn't swear to it.
Okay. Okay. So we'll go with that. Quadruple 0, 9, 2, 8. Okay, we're allowed 2 sig figs. Now we have to justify our assumption. So let's go ahead and do that next. How do we justify the assumption? We calculate the percent change. What is the percent change going to equal in this case? It'll be equal to the change. What is the change? X or 2x? The change, x or 2x? The change is actually 2x this time rather than x. Sometimes it's 3x. It depends on the equation. Over the original is 0.100 of initial. It's 0.100 times 100%. And so what does that come out to? 2 times that divided by 0.1 times 100. $1.85%. Is that right? Yes? Seems a little bit off.
I I got one.
0.18 sounds better. Yeah. 0.185%. And so what do you think? Is the simplifying assumption going to work better this time? Yeah. I think it's going to work a lot better because it's a lot less than 1% change. And so are we okay? Yeah, this is less than 5%, so it's justified. It sure made the math a lot easier, didn't it? Because what would I do if this failed? I couldn't use the quadratic. I can't use the quadratic because it's a qubit. Run to the store and buy one of those calculators? Is that what you're going to do? Well, one of those calculators isn't required. So you should still be able to solve this. We have one more fallback method. The fallback method is, have you ever heard of the method of successive approximations? It's discussed in Appendix A. And the method of successive approximations is just a guess and check method. And so all we're going to do is we're going to start guessing values of x, plug them in here, and see if it comes out close to 3.2 times 10 to the minus 10. And keep guessing until we hit 3.2 times 10 to the minus 10. That's the method of last resort there. But, you know, we aren't guessing at any old number because x cannot be less than 0, right? They give you a negative number here. And it cannot be greater than 0.05 because if it's greater than 0.05, this would come out negative. And so we just have to guess an x value between 0 and 0.05. Guess that and then plug it into our original equation until we get this. So that would be our fallback method. But we don't have to use that because the justification was okay. And we're going to go ahead and calculate our concentration. And so even though we said 2x is negligible, now we don't want to add another error by doing that. We're going to go ahead and calculate it. And so it's going to be 0.100 minus 2x. Two of these would be 185, is that right? Yeah. 0.123185. Is that right? Okay. And so this comes out to 0.099815 molar. And so,
So are you assuming that the minus 2x just drops because of the
no, we assumed it just to calculate x, but once we have an x value, we don't drop it out. You see, here's my 2x right here. And so, I get rid of it one time to calculate my x, and then all of a sudden I say, wow, it's significant now, right? Before I said it's insignificant to calculate x, and now I'm saying it's significant, we better include it. You see? And the reason is it's better because it leads to smaller error. Because if you say it's insignificant then, and it's insignificant now, that's double error, compared to saying it's insignificant then, now it's significant. And that's going to lessen the error.
So you're dropping the initial 2x in substitution of a quadratic formula, right?
I'm dropping this 2x here. Do you see? I'm saying it's insignificant here, so 0.100 minus 2x is just equal to 0.100. And this is just to make the math a lot easier, because now I don't need anything. You need the cube root key on my calculator. And so I calculate my x here. But once I get my x, then I say, wow, I'm not going to ignore it. I'm going to go ahead and factor it in. A lot of people will say, well, I ignored it once, I'm going to ignore it again. You can't do that. What we're going to say is we ignore it once, now it's important. And why the 180 shift? The 180 shift is because this is going to be a better answer than 0.100. Because if you leave it at 0.100, you're saying nothing reacted. Nothing reacted. Well, something did react. Only 0.2%. 0.2% is not no reaction, is it? I mean, I guess it depends on your context. If it's Chem 1A, you could say no reaction because that's so little. Right? In Chem 1B, well, 0.2% is a little bit, and so it's significant. And so X here, this is going to equal 0.000928 molar. And 2X here will equal 0.000185 molar. Was this 5 rounded or not rounded? It was rounded? We're not allowed to round, huh? It was 4? Okay. Yeah, unfortunately we can't round that, so let's not round it. If it's 4, let's leave it. It's 4, so that's going to change this to 6. We're only allowed one rounding step. Is that right? Was it 4? No, it should be 6. If I double this. But it depends on how many digits you carried in this. If you carried it and then doubled it, you get a different answer than if you chopped it off and doubled it. All right, I'll just leave it. Whatever. All right, now let's double check our equilibrium concentrations. I'm expecting this double check to come out closer to 3.2. Times 10 to the minus 10. And so K is going to equal 0.000184 squared. Oops, times lead, sorry. Lead gets in here. 0.0928 divided by 0.099816 squared. So it's the lead concentration times the chromium concentration squared divided by the chromium concentration squared. What does it come out to? Times 10 to the negative 10, which this would round to 3.2. And so, is that a pretty good? Yeah, that's pretty good. So when the percent change is very small, the simplifying assumption works pretty well, you know. But as that percent change grows, then it's a judgment call. But we're allowed to 5%, so we're going to introduce quite a bit of error going out to 5% there. All right, let me stop here. We'll take a break and then look at some more calcs.